And if we think about finite geometry in general, then finite geometry in Italy, I think, can be traced back to 1954 by a paper of Beniamino Segre's, and the tradition there has continued ever since. And so I'm very pleased to introduce this morning Daniele Bartoli from the University of Perugia, who's going to talk to us about Hasse-Weil type theorems and relevant classes of polynomial functions.
Okay, thank you, James. Thank you so much for your kind introduction. And can you hear me?
Yes.
Okay, perfect. So first, let me thank the British Combinatorial Committee for this invitation. It's a big honor for me to be here. Now, as you can see from this first slide, I would like to talk about connections between relevant classes of polynomial functions or combinatorial problems and algebraic varieties over finite fields. So, first, I will recall a few basic notions about the easiest non-trivial example of algebraic varieties in finite fields, which is given by plane algebraic curves. Then I will present a few examples in which we can see how to attach to a specific polynomial problem an algebraic variety. And then I will talk about the possible machineries or techniques in order to study such varieties and then to get answers for your starting problem. We will see applications of this method to, for instance, permutation polynomials, planar polynomials, or scattered polynomials. Well, all these classes of functions and many more are related, I can say are strongly related to more applied areas of mathematics like coding theory or cryptography. For instance, permutation polynomials are connected with S boxes or public key cryptography, but also coding theory and orthogonal Latin squares. Now, planar polynomials in both Q even and Q odd case are related with relative different sets, error correcting codes, and again cryptography. Scattered polynomials are related with a variety of objects, like objects in finite projective spaces like blocking set, small complete caps, and translation hyperovals, but also coding theory. So two intersection sets which correspond to two-weight codes, MRD codes, but also algebraic structures like finite semifields. Well, now let's start from this basic example. So suppose that we have a polynomial f of x, which is defined over fq. So all its coefficients are in fq. And we would like to know if such a polynomial permutes fq, which means if it is a bijection seen as a function over fq. Well, it can be easily seen that this is equivalent to ask that for each b in fq, the equation f of x equal to b has exactly one solution x bar in fq. This is for any b. Well, this is equivalent to ask for this bivariate equation f of x equal to f of y, having just one solution for each x bar. Yeah, so basically it has only solutions of the type x bar comma x bar with x bar in fq. Well, since f of x minus f of y is divisible by x minus y as a polynomial, we can just rephrase this saying that f of x minus f of y over x minus y, this bivariate equation here, has no solutions x bar y bar apart from the trivial ones, which are those with the two entries which are the same. Now, this equation here defines, as we will see in a few minutes, a plane algebraic curve. And solutions of this type, so pairs of elements of fq, will be fq rational points of such curve. Now, let's see an example. So suppose that we would like to know if this guy here, x cubed plus x, permutes F7. F7 is the field with the 7 elements, so 0, 1, 2, up to 6. Well, if you remember what I said in the previous slide, we have just to check if this bivariate equation has solutions which are non-trivial, so with x different from y. Well, you can even do it by hand, so you end up with these 6 solutions. Now, let's just remove the 2 solutions 4, 4, and 3, 3, which are not suitable for us, but still we can find solutions with x bar different from y bar. And so we can conclude, if you remember what I said before, that this guy does not permute F7. Clearly, this is easy, an easy example, so you can even do it by hand. This is just to show the connection between a permutation polynomial and a bivariate equation. Now, this is not the first time, clearly, that you can attack a certain problem using algebraic varieties. One of the first times that this approach appeared in the literature, at least up to my knowledge, dates back to the 70s, when Beniamino Segre and Lucio Lombardo Radice were interested in constructing so-called small complete arcs in projective planes. What is an arc? Yeah, an arc here is a set of points, no 3 of which are collinear. And such an arc A is called complete if for each point P, which is outside your arc, you can always find a line through it containing 2 distinct points, Q1 and Q2, in your arc. The idea of Segre and Lombardo Radice was to construct the arc taking the points, the FQ rational points of a certain low degree curve, usually a conic or a cubic curve. And the connection between algebraic curves over finite fields comes when they wanted to check if a point P, which is not in the arc, is covered or not by the points of the arc. So they could attach to each point P in blue a certain curve, let's call it CP, in a way that if inside this curve there is a point which is FQ rational, so it has coordinates in FQ, then this means that you can find a line through P intersecting your arc in 2 distinct points, Q1 and Q2. Clearly, you have to check these for each point. So basically, you have to study not just one curve, CP, but a family of curves which depend on the 2 coordinates of the point P. Well, using this approach and clearly modifications of it, people could also study generalizations of complete arcs in projective planes, that is, complete arcs in projective spaces, or complete caps, or planar K arcs. Well, all these objects are not just interesting from a theoretical point of view, but they have also nice connections with, for instance, coding theory, since, as you maybe know, complete arcs in projective spaces, they correspond to MDS codes that are the best codes with respect to the singleton effect. Now, let's go back to the main topic of this talk. So first, let me recall a few notions about a curve. Here, I would say something just concerning plane curves. So the setting in which I will consider such curves is the affine plane, which is just the set of pairs of elements of FQ, or the projective plane, which is the larger set of points which contains the affine plane plus the line at infinity, this special line. Well, in this setting, a curve is just a class of proportional polynomials into variables x and y with coefficients in FQ, where the degree of the curve is just the degree of the polynomial f defining the curve. For instance, if the characteristic is not 2, I would like to identify the curves arising from these 2 polynomials. And that's because I have in mind also the solutions of the equation f of x and y equal to 0, which is clearly the set of solutions is the same for this guy and this guy. So I call A and B a point in the affine plane and FQ rational point of my curve if it is a solution of the bivariate equation f of x and y equal to 0. Now, clearly you can consider FQ squared rational points, FQ cube rational points, meaning that the two coordinates A and B, they can be in an algebraic extension of FQ, but the curve still is defined over FQ, which means that the polynomial f has all its coefficients in FQ. Now, a key point when you want to study algebraic varieties in order to get answers for your starting combinatorial problem is to deal with the absolute irreducibility of your curve. So this means that your polynomial f of x and y cannot be factorized into two polynomials g and h of positive degree, even if you allow the coefficients of g and h to be in any algebraic extension of the finite field FQ, namely in the algebraic closure. So for instance, if the characteristic is not 2, then this polynomial x squared plus y squared plus 1 defines an absolutely irreducible conic. And but this guy here, so if you pick up an element S, which is a non-square in FQ, then it cannot be factorized if you allow the coefficients of the two putative factors just to be in FQ. But if you consider eta, the square root of S, which lies in FQ square, then you can actually factorize this guy into these two factors, which tells you that your polynomial x squared minus sy squared is not absolutely reducible. Now, a key point, as we will see in a few minutes, will be to count, or at least to provide a lower bound on the number of the solutions of the bivariate equation f of x and y equal to 0. That is, to provide lower bounds on the number of FQ rational points that a certain curve can have. And a milestone in this direction is the celebrated Assevel theorem, which states that if your curve is absolutely reducible, I wrote it in blue, and suppose that it has degree d, then the number of FQ rational points in the projective plane, but in the affine plane they are roughly the same, is very close to Q, with an error term here of the type square root of Q times d squared. So I have to point out two things. First, as I already mentioned, the absolute reducibility of this curve is very important, because otherwise you can find examples of curves which are not absolutely reducible, but have more points than the upper bound here, or less points than the lower bound. So it is crucial to have the absolute reducibility in order to get this bound here. But also, since we are always interested in lower bounding the number of FQ rational points, we can deal with curves having small degree. When I say small, I mean smaller than the fourth root of Q. Otherwise, the lower bound here, the error term here, is larger than Q, so the lower bound is negative. And this tells you nothing about the existence of putative FQ rational points inside your curve. So let's come back again to our toy examples about permutation polynomials, so we can rephrase what we said at the beginning in this way. F of x is a permutation of FQ if and only if this curve here in red, CF, this is, I didn't mention, but this is actually a polynomial. It's written as a rational function, but the numerator is divisible by the denominator. Yeah. So if and only if this guy, this curve here, has no affine FQ rational points outside the line x equal to y. So if you remember, we just studied x cubed plus x over f7 at the beginning. Now we can just study the permutational properties of this polynomial over any q, just looking at the curve arising from the polynomial f. If you do the computation, as we already saw over f7, you end up with this degree 2 curve, which is conic, which is absolutely reducible, and it is well known that each conic, in this case, has precisely q plus 1 FQ rational points in the projective plane. Now, if you remove the at most 2 points at infinity and the at most 2 points on the line x equal to y, you end up with at least q minus 3 FQ rational points of the type x and y, that is affine, and not lying over the line x equal to y. This means that actually, if this guy here is positive, that is q is larger than 3, then your polynomial is not a permutation, because you can find FQ rational points on this curve, which are non-trivial. So the connection is very easy in this case, but actually you can use this approach using algebraic curves, not just to say that something is not the permutation, but also to provide a complete classification for the fields in which it permutes or not the set of elements. Well, suppose that we want to study this polynomial, so x7 plus x5 plus x. We are over a field in characteristic 2. Well, let's write down our favorite curve. Now it's a degree 6 curve. And I don't know if you can do it by hand, but trust me, this polynomial of degree 6 factorizes into 3 absolutely reducible polynomials of degree 2, which define 3 conics. Now, here omega is an element of f8, yeah, which satisfies this. So in general, these 3 conics can be defined or not over the field we are interested in. In particular, if 3 divides k, f8 is a subfield of this. So this means that each of these 3 conics is defined over the ground field f2 to the k. And so, as we saw just before, each of these conics possesses actually FQ rational points, and so we can conclude that this guy is not a permutation. On the other hand, if 3 does not divide k, which means that f8 is not a subfield of this guy, so each of these conics is not defined over the ground field f2 to the k, then we can easily check that each of these conics has no FQ rational points outside the line x equal to y. And so we can conclude, using the connection between algebraic curves and permutation polynomials, that this guy actually is a permutation. So in some cases, we can answer completely to our question about the permutational property of a certain polynomial. Well, in the literature, you cannot find too many criterions telling you if a certain curve is absolutely reducible. One of the first that I know is due to Segre, which in the 70s was still interested in constructing small complete arcs from cubic curves. And actually he used this criterion in order to show that a certain subset of points is actually an arc, a complete arc. Well, this criterion says that if you have a curve in blue and you can find a point P, this point must be not FQ rational, it can be in the algebraic closure in general, but the important fact is that you can find a tangent line through it, which is non-repeated among the set of all the tangent lines to it. And this line intersects your curve at just this point P. Then, if these two things happen, you can say that your curve is absolutely irreducible. So it's very specific, and usually you cannot apply this criterion to your curve. But as we will see in a few moments, it's not necessary in general to have the absolutely irreducibility of your curve. In many applications, you just need to prove the existence of components of your curve which are absolutely reducible and defined over graph Q. To this end, let me introduce the Frobenius automorphism, which is just a function from the algebraic closure of Fq to itself, which sends an element alpha to its power Q. Clearly, it can be extended, I use the same notation, to a function from the affine plane, so taking pairs of elements alpha and beta in Fq bar, and taking the Frobenius of each coordinate, but also it can be extended to polynomials in the two variables x and y, just taking the Frobenius of the coefficients. Now, it is readily seen that if you have an element of Fq, then Φq fixes such an element. And also it fixes points in the affine plane over Fq, because it fixes pointwise the entries. And also, we say that a certain curve is fixed by the Frobenius if the polynomial defining it is defined over Fq apart from a multiple scalar lambda, which can be in the algebraic closure. Clearly, it must be different from 0. Now, let's have a look on how the Frobenius acts on the components of a certain curve. So we start from a curve which is defined over Fq. Now, if it is not absolutely reducible, then the defining polynomial f splits into, let's say, k factors, which are absolutely reducible, and in general, their coefficients are in the algebraic closure of Fq. Then each of these factors provides a component of your curve. Well, since the starting polynomial f of x and y has coefficients in Fq, if you have a solution P of the equation f of x and y equal to 0, that is an Fq rational point, or in general, if you have any point of your curve, then if you apply the Frobenius sends this point, this solution, to another solution of the equation f of x and y equal to 0. So the Frobenius acts on the points of the curve in the algebraic closure, but also it acts on the components of the curve. In general, it interchanges the components Ci and Cj. But if one component Ci is fixed by the Frobenius, then we say that Ci, which is clearly defined over Fq, it means that the polynomial Fi, apart from a scalar multiple, has all its coefficient in Fq, then we say that Ci is absolutely reducible Fq rational component of the starting curve. Why is it important to know if our curve perhaps is not absolutely reducible, but it possesses absolutely reducible components defined over Fq? Well, let's see an example. So suppose that we would like to know if x to the power 6 permutes the field F23. Clearly, you can check that this is not true because 6 is not coprime with 22. But let's see what happens to the curve. Well, the curve attached to x to the power 6 reads as follows. So you have a degree 5 polynomial, which actually factorizes into 5 factors, which are linear factors, where alpha is a 6th root of unity, which usually lies in the algebraic closure of F23. Now, alpha cubed is -1. So this line here, this degree 1 polynomial, is actually defined over F23. And so it has a exactly 22 F23 rational points if you remove the origin, which is the unique point on this line for which the two entries, the two coordinates are the same. And so using the connection we saw many times between permutation polynomials and algebraic curves, we can conclude that actually x to the power 6 is not a permutation. As I mentioned, this is clearly very easy to check in other ways, but this is the connection with algebraic curves. And actually we can extend this connection to any permutation polynomial or putative permutation polynomial. So using Hasse-Weil theorem, we can actually prove that in a small degree regime, that is the degree of f is smaller than the fourth root of q, then if f is a permutation, our favorite curve CF has no absolutely reducible components defined over fq apart from perhaps x minus y equal to 0. The proof is very easy. I just would like to say a few things. Don't look at the details, just at the idea. So suppose that this curve CF has, let's say, D, an absolutely reducible component defined over fq. Then apply Hasse-Weil to this guy. Since the degree of D is smaller than the fourth root of q, using Hasse-Weil, the number of fq rational points of D in the projective plane is positive. Now, if you even remove the possible points at infinity and on the line x equal to y, you still end up with a positive number of fq rational points which are affine and not on the line x equal to y. This means that your starting polynomial is not a permutation, which is clearly a contradiction because your hypothesis was that your polynomial was a permutation. So this is a connection between permutation polynomials and components of the curve CF. Now, interestingly, there are a little bit more criterions that you can find in the literature in order to show that something, a certain curve, possesses an absolutely reducible components defined over fq. I would like to show you just this, which is very easy. But first, let me recall that the simple point of a curve is a point such that the derivatives of the defining polynomial f of x do not vanish at the same time on the coordinates of P. Now, if you have a simple point, then this simple point belongs to a unique component of your curve C. So the criterion is the following. Suppose that you have a simple point of a curve, which is also fq rational. So its coordinates are in fq. Then C, the curve C, possesses an absolutely reducible component defined over fq. We just have to apply the ideas coming from the Frobenius morphism. So you have a point which is fq rational, so it is fixed by the Frobenius. Now, we already know that there is a unique component of C through P, and let's call it D. If you apply the Frobenius to the component D, you end up with a component passing through phi q of P, which is P. So both phi q of D and D pass through the point P, which is not possible unless these two guys are the same. So basically you show that this component D is fixed by the Frobenius, so it is defined over fq, and that's the end of the story. Clearly, this is very easy, but actually in few applications, you could apply these criterions in order to show that your favorite curve possesses an absolutely reducible component defined over fq. Well, let's go a little bit further. So, as I mentioned, the two key points are the absolute reducibility of the variety in general of the curve that you are interested in, but we saw a few ways in order we can bypass this problem. But also, another fundamental problem is the degree of the curve, because even if you prove that your curve possesses an absolutely reducible component defined over fq, you still need Hasse-Weil or modification of Hasse-Weil as a veil bound, but they need a low degree, so smaller than the fourth root of Q. But actually, there are a few cases in which you can bypass this problem. So, using criterions or other ideas. If a polynomial f is such that f of 0 is equal to 0, and up to translations you can always assume it, then it can be written as x to the power r times h evaluated in x to some power here, where this power is the divisor of q minus 1. F was a polynomial defined over of q. Well, this criterion says that a polynomial written in this form is a permutation if and only if these two conditions hold. So R is co-prime with this inner exponent, and a slightly different polynomial, here the exponent is inside, here it is outside, permutes not fq, but a subset of fq, namely the set of the deep roots of unity, which is completely contained in fq, because this guy is a divisor of q minus 1. Well, so let's see how we can use this criterion in order to study a simple curve, at least an attackable curve. Well, suppose that you would like to classify all the pairs alpha and beta in fq squared, q is a power of 2, such that this trinomial here is a permutation of fq squared. Well, now let's apply the previous criterion. So it tells you that f alpha beta permutes fq squared if and only if g alpha beta, this other guy, permutes a smaller subset, so mu q plus 1, the q plus 1 roots of unity, so it's smaller, but the shape of this guy is ugly, okay? It's not much better, and also the degree is very high, as you can see here. I didn't mention, but you cannot apply directly the connection between a permutation polynomial and an algebraic curve in this case, because if you see the degree of the curve you have to study is roughly q squared, that is the size of the field. So it makes no sense to study directly the curve attached to this guy. But the situation does not improve here because the degree of G is still very high. But now you can just use this correspondence between an element of fq squared and pairs of elements of fq, using this I, which is a certain fixed element of fq squared. But more interestingly, you can parameterize each element of mu q plus 1, different from 1, using an element x prime in fq. And now, if you plug in all these guys here inside G alpha and beta, quite surprisingly, you end up with a rational function that is numerator and denominator, but with the feature that both numerator and denominator, they have very small degree. And this guy, this rational function, is now defined over fq. And G alpha and beta permutes mu q plus 1 if and only if this rational function here permutes fq. Now, we saw the connection between permutation polynomials and algebraic curves, but there is also basically the same connection between permutation of rational functions and algebraic curves. And so to this guy H, you can associate a certain curve here, which has very low degree, at most 4. And the connection is the following. Your starting polynomial f alpha and beta is a permutation of fq squared if and only if this curve, which is attached to your guy here, has no fq rational points apart from those possibly on the line x equal to y. So formally it's the same connection, but now the degree of this curve C is 4, and the degree of f here was roughly q squared. So using this approach, actually you can completely classify pairs alpha and beta for which this curve has your favorite condition, and so this guy is a permutation. Now, we saw connections between algebraic curves, plane algebraic curves, and permutation polynomials. This is not always the case. I mean, for other classes of polynomials, you have to attach more sophisticated algebraic varieties, and one of the easiest case, which is not given by plane curves, is provided by surfaces in projective spaces of dimension 3. Let's start from a few definitions. So a planar function, if Q is odd, is a function defined over Q for which, for any epsilon non-zero, the derivative with respect to epsilon, which is given by f of x plus epsilon minus f of x, is a permutation. This is for any epsilon. Now, they have been introduced by Dembowski and Ostrom to study finite projective planes, but they've been found to have nice and deep connections also with different areas of mathematics, like relative difference sets, error correcting codes, and again, cryptography. Now, if Q is even, you can easily check that the derivative f of x plus epsilon minus f of x can never be a permutation. The best that you can have is that it is a 2-to-1 function. Well, so in 2013, Yu Zhou modified the definition for Q even of planar functions, basically just adding this extra term here, epsilon x, but the assumption is again that for any epsilon non-zero, this guy here is a permutation. Well, quite surprisingly, these planar functions can be considered as really the Q-even counterpart of planar functions in odd characteristics, since apart from the connection with projective planes, they can be used in order to construct relative difference sets, error correcting codes, and they also have connection with cryptography. Now, from the definition here, you can easily see that if your polynomial f is linear, I mean linearized, that is, all its monomials are a degree, a power of 2, then this quantity here reads epsilon x plus f of epsilon. Since epsilon is different from 0, it's a linear function, which is always a bijection. So linearized polynomial, that is linear mappings of the finite field FQ, always provide planar functions. And together with the Caillou-Schmidt, we could actually prove the converse clearly in small degree regime, always smaller than the fourth root of Q. This should recall you that the use of Assebel theorem or Assebel type bounds. So our main result was the following: f of x is planar if and only if it is 2 linearized, clearly if the degree is small. And the idea was to attach to our function not a curve but a surface. So a variety defined by a polynomial in 3 variables, x, y, and z. The setting now is the projective space or the affine space in dimension 3. So points are triples of elements of FQ. And the connection is the following: f of x is planar if and only if this guy here, s of f, has no affine FQ rational points apart from those lying on the planes x equal to y and x equal to z. Now, in order to prove our results, we starting from a polynomial f, which was not linearized. In this case, the surface s of f is non-trivial. Then we cut this surface with a specific plane defined over FQ, and so we find the intersection, which is a plane curve now. And now, using local quadratic transformations and investigations of singular points of this curve CF, we could actually prove that this curve CF as an absolutely reducible component defined over FQ. Now, this curve is completely contained in SF. So, using Asserville theorem, we could prove that this curve CF possesses absolutely reducible, FQ rational points, not on the forbidden planes, and so this happens for the starting surface SF, and so we can conclude that if Q is large enough with respect to D, our surface possesses suitable FQ rational points, and so F is not planar. So again, the connection is not between plane curves, but between another type of variety of finite fields. But the situation, clearly the machineries that you can use strictly depends on curves inside your surface. Now, in this last part of my talk, I would like to talk about another method which provides the existence, in some cases clearly, of absolutely reducible components defined over FQ for plane curves. Yeah? This method has been introduced by Yanua, McGuire, and Wilson some years ago. They wanted to study so-called O polynomials, but later on, the same method, or modifications of it, has been applied to deal with planar polynomials in both Q, even and odd characteristics, APN functions, and also scattered polynomials, as we will see in a few minutes. So, the idea is to provide contradictions counting in a certain way the singular points of a certain curve and using Bezout's theorem. So, suppose that you have a curve which is defined over FQ, and let's say that its degree is a certain integer d. Well, also suppose that it has no absolutely reducible components defined over FQ. So in particular, it is not absolutely reducible. Now, this means that the polynomial f of x and y can be factorized in many factors. Now you can manage in order to put all together a few of these factors and divide them into two big factors, capital A and capital B, in a way that the degree of A is very close to the degree of B, namely the product is larger than 2d squared over 9, where d, I recall you, it's the degree of the starting curve C. Now, these two components, A and B, they are not absolutely reducible, clearly, because they usually are, they are union of components of the starting curve C, but they intersect at singular points of the starting curve C. Now, if these two components, A and B, do not share any component, then Bezout's theorem says that the product of their degrees is precisely the number of intersection points counted with multiplicity, where the multiplicity is given by the intersection multiplicity of the two components at the point P. Now, clearly, P runs among the intersection points, but in the algebraic closure and in the projective plane. From one end, we have that this guy is lower bounded by 2d squared over 9. On the other hand, sometimes you can provide nice upper bounds on this integer here. Let's call it max p, where p is again a point of the intersection. And sometimes you can see that actually the upper bounds you provided give you a contradiction, since if you sum all these upper bounds on the points, on intersection points of A and B, then you obtain something which is smaller than 2d squared over 9. And so by this chain of inequalities, you your desired contradiction. So your curve actually possesses an absolutely reducible component defined over FQ. What are the problems of this approach? Well, first, your curve is not specified usually. So it contains many parameters depending on the starting polynomial or the starting problem that you have in mind. Secondly, you clearly have no idea about the two putative components A and B. Also, you have no idea where they intersect. So basically, you have to consider these upper bounds for all the singular points of the starting curve C, which is usually a set much larger than the possible intersection points of A and B. And secondly, you must have both an upper bound on the number of singular points, because otherwise you cannot get this contradiction, but also you must have a nice upper bound here, which is not so easy. And usually you can provide, you can have information just studying the tangent cone at singular points, or for instance, using branches. So showing that, for instance, there is a unique branch centered at a certain singular point, or again, studying branches and their structures, you can provide upper bounds which are suitable for you getting this contradiction. Well, let's see an application to maximum scattering linear sets in this final part of my talk. So I don't know if you attended the talk of Ferdinando Zullo and also the talk of Giovanni Zini. They spoke about generalizations of scattering linear sets in the projective line. So maybe you already know these definitions, but let me recall a few basic notions we will use in the next few minutes. So the projective line over FQ to the n is just the set of pairs of elements of the ground field FQ to the n, clearly apart from the zero pair, and they are defined up to a scalar multiple. Now, consider the vector space FQ to the n squares, so pairs of elements of FQ to the n, and consider a vector subspace U, which is an FQ vector subspace, and let's say that its dimension over FQ is K. Now you can consider the elements of U, which are pairs of elements of FQ to the n, and see them as points in the projective line over FQ to the n. And we call such L of U an FQ linear set of the projective line of rank K, where K is just the FQ dimension of the vector subspace U. Now, in the case of dimension n, so rank n, you can describe all the vector subspaces U in this way: x comma f of x, where x runs over the field FQ to the n, where f of x is a Q linearized polynomial, that is a polynomial having Q having as degrees of the monomials just powers of Q. Now, we say that L of U is a maximum scattered linear set of the projective line if the dimension of U, the Q dimension, is n, and L of U possesses the largest possible number of points, that is Q to the n minus 1 over Q minus 1. In this way, the f, the linearized polynomial f, which provides the parametrization of U, is called, using a terminology introduced by John Shiggy in 2016, is called scattered polynomial. Well, actually, we can a little bit generalize the parametrization of U, just allowing the first coordinate to be a Frobenius of x, so x to the power Q to the t. And if the corresponding linear set is a maximum scattered linear set, we say that the Q linearized polynomial f of x is scattered of index t. T is this guy. So scattered polynomials are scattered polynomials of index t in this new definition. Well, the connection between scattered polynomials of index t and algebraic curves is provided by Yes, it's provided by the following lemma. So, sorry. Okay, no, I thought that there was some problem. Okay, so the connection is the following. Your guy is a maximum scattering linear set if and only if this curve has no fq to the n rational points whose coordinates, the ratio of their coordinates, is an element of fq. Okay, so basically all the fq to the n rational points of this curve, they lie on lines y equal to lambda x, where lambda, the slope, is in fq. And using this connection, that is studying this curve here, together with Joe, we could provide a classification for scattered polynomials of degree 0 and 1, finding that there are just monomials or so-called LP polynomials, or binomials of this type. Well, our main tools were clearly the method I just introduced by Yanwa, Maguire, and Wilson, and clearly we had to investigate very deeply the branches centered at singular points of this curve. And actually, just very recently, together with Maria Montanucci, we could classify the case t equal to 2, finding just monomials or binomials of LP type. Let me just mention that using a connection with Galois theory, recently Micheli and Ferragutti provided classification in the case in which the maximum between t and the q degree of f is a odd prime, finding no other examples apart the monomials one. Well, so this is the final slide of my talk. I just presented a few connections between problems arising from polynomials or combinatorial problems, let's say, and algebraic varieties over finite fields. But together with my co-authors, we could attack also other different problems connected with other objects. So, for instance, objects in finite projective spaces like arcs, caps, or semi-ovals or blocking semi-ovals, but also ovoids of Q4Q, Q5Q, and Q6Q. We could also study problems connected with the graph theory, so resolving sets in specific graphs, clearly permutation polynomials and polynomials with low differential uniformities, so PN, APN, but also generalizations of them, APCN, for instance, Kloosterman polynomials, and finally, scattered linear sets and other generalizations of these objects, and clearly the algebraic structures like Moore exponent set, which are connected with MRD codes, perfect linearized polynomials, and so on. So that's basically what I wanted to say. So thank you for your attention.
Thank you, Daniele, for the very clear slides and good explanations. Does anyone have any questions for Daniele?
I have some questions. May I ask?
Yeah.
Can you hear me, Daniele?
Yes, yes.
Thank you very much for your very nice talk. So I'm not expert in algebraic geometry. I touched the algebraic geometry recently, quite recently. I'm working in graph theory. But the point is that I was, as Olympiad student, I was interested in this Fermat-Less theorem and this elliptic curve. So I missed somehow what is the difference between these two. And so you consider a general curve, yes? It is not indeed elliptic curve, am I right?
Yeah, in general, no. I mean, it depends on your problem, but usually it's not a curve of genus 1, so it's not an elliptic curve in general. So these machineries, they work for general curves.
So this is it is somehow a generalization of that ideas of elliptic curves?
No,
Can we say?
I mean, I don't know if there is, I don't think that there is a connection between how elliptic curves have been used in order to deal with Fermat's last theorem and what I presented. It's a different, yes, a different approach. So this, I mean, they are not connected. They are clearly, they are curves, but the feature that you need from those curves, I guess they are completely different. Here, I'm interested on curves over finite fields, and I would like to know if they possess suitable FQ rational points, which is actually, I guess, a little bit different from what you need in order to prove Fermat's last theorem.
But sorry to say that many tools are very similar. For example, you had no page numbers for your talk. So you mentioned these two Italian guys. So I know from the history that Italian has very long history of this algebraic geometry. So you mentioned this intersection of this circle and a line intersect the circle. Am I right? I don't know which number of the pages is. So
okay.
this idea. So this idea is, as you mentioned, is exactly the same idea for assigning a group to elliptic curve. Because when you wanted to define this abelian group associated with an elliptic curve, you use the same idea. It means that these Italian guys, I don't know, independently use the same idea of associating a group, abelian group to elliptic curve. Maybe it is just similarity. But I have other similarity I'm saying. You use this divided difference f of x minus f of y over x minus y. So in a proof of Fermat's last theorem, they use a similar divided difference, which is called the Q version. Because if you define the permutation over elliptic curves, the denominator is x to the q minus x because of the Fermat little theorem. And instead of x minus y, you have x to the q minus y or x to the q minus x.
Okay.
So, I mean, there are many similarities between tools in Fermat's last theorem and very nice idea that you mentioned. So I just, maybe it is as even the theorem of Weil-Haas, we have the similar theorem which says that the number of rational points minus the absolute value of number of rational points minus q plus 1 is less than 2 square root of q. And this 2 square root of q also appears in a spectral graph theory, in let's say this graph, expander graphs. So very similarity with, it seems that it is going parallel. And you just change the divided difference that I know from discrete derivative in combinatorial setting.
Okay, I was not aware of.
I will write to you, I think, but I really enjoyed because of this parallel similarity. Of course, from my point of view, as not expert in this area, just interested to, as Olympiad student, to read the proof, some part of the proof. Thank you very much for your very nice talk.
Thank you so much.
Are there any other questions? No, well, let us thank Daniele again for a very nice talk.
Thank you. Thank you.
Very nice talk.
So now we can take a break before the next session.
There are questions.
There are questions.
If you want to stick around for further discussion,